Welcome back, student. Now today we'll take an example or numerical on psychometric relation, and in the previous lecture video we already discussed on the psychometric relation like relative humidity, specific humidity, and some degree of saturations, and obviously the enthalpy of moisture airs. Okay, so all these topics we will already cover on this. Now today we'll discuss on this type of numerical. Now the problem suggests that the reading from a sling psychrometer are as follows. Dry bulb temperature is 30 degrees centigrade, wet bulb temperature 20 degrees centigrade, barometer reading 740 millimeter of Hg. Now using steam table determine the dew point temperature, okay, the dew point temperature, the relative and specific humidity, degree of saturations, vapor density, enthalpy of mixture per kg of dry air. So in this numerical, basically, as you know that sling psychrometer is basically used to determine the temperature of wet bulb and dry bulb temperature. Okay, means DBT and WBT. So the reading from a sling psychrometer are given as follows: that dry bulb temperature is given as like 30 degrees Celsius and wet bulb temperature is 20 degrees Celsius. Okay, now that barometer reading 740. It's given, that is barometer reading means that is PB here. Barometer reading, that means here PB it is given. Okay, I know that from the Dalton's law, partial vapor pressure, that is PB is partial barometer reading PB is equal to PA plus PW. PA plus PV. Okay, now barometer reading is 740 millimeter of Hg. Now using steam table, first we will determine the dew point temperature, that is nothing but dP, also written as dew point temperature. Okay, relative and specific humidity, degree of saturation, vapor density, and enthalpy of mixture per kg of dry air. So all these terms you have to calculate. Now in this problem, what is given, that TD is basically given as 30 degrees centigrade, means dry bulb temperature. Wet bulb temperature is given as 20 degrees centigrade, and PV means barometer reading is given as 740 millimeter of Hg. Okay, now you have to calculate the dew point temperature. Okay, now when you calculate the dew point temperature, so corresponding dry bulb temperature, wet bulb temperature, and barometer reading. Okay, this is a barometer reading. Now let's find the partial pressure. First you have to calculate the partial pressure of water vapor. So first you have to find the partial pressure of water vapor, that is PV. Okay, now from the steam table, from your steam table, if you go to the saturation steam table of water, okay, for corresponding temperature scale, for the 20 degrees centigrade, we can get the value of PW here, that is 0.02337 bar. Okay, now PV is given as your barometric reading, that is 740 mm of Hg. You just convert into mm of Hg is into bar. So 740 mm of Hg is transformed into 0.986 bar. Okay, now you have to first, because you have to calculate, because you determine the dew point temperature means first you have to calculate the partial vapor pressures. So when you calculate the partial vapor pressure, so corresponding partial vapor pressure, because the dew point temperature is basically the saturation temperature. Means dew point is the saturation temperature corresponding the partial pressure of water vapor. So that is because TDP is the saturation temperature. Okay, TDP is the saturation temperature corresponding to the partial pressure of water vapor. So if you know the value of PV, means partial vapor pressure, so corresponding PV value from the steam table temperature scale, you can get easily the value, the dew point temperature. Okay, now PV is equal to, as you know that PV is equal to PW, because we already calculate the pressure, vapor pressure. So PV, as you know that PW minus PV minus PW into TD minus TW divided by 1544 minus 1.44 PW. So as you know, PW is your basically the corresponding wet bulb temperature, that is pressure, that's PW. PV indicates the barometer reading, that is 740 mm of Hg, which is converted into your bar, the value. Okay, that is 0.986, and TD is your basically dry bulb temperature, TW is your wet bulb temperature. Okay, now TW is your wet bulb temperature. If you put all this value PW in terms of your 0.986, PV is your PW is basically your 0.02337 and PW is your 0.986 and TD is your 20 degrees Celsius and TD is basically 30 degrees centigrade and TW is your 20 degrees centigrade. If you put all these values here and TW in terms of 20 degrees centigrade also, then you can get easily value the PV. If you get the value of PV, as you know that the dew point temperature is the saturation temperature corresponding the partial pressure of water vapor. That means if you know the value of PV, then corresponding steam table temperature scale, if you use your steam table, go to the steam table and the corresponding steam table or saturated water scale, saturated water table, then from corresponding the value of temperature, that you can get the value of TDP, that is 15 degree centigrade. And the next we calculate the relative and specific humidity. Okay. So in the second part of the numerical, you have to calculate the relative and specific humidity. Okay. So when you calculate the relative and specific humidity, just a minute. When you calculate the relative and specific humidity, so from the steam table, okay, because relative humidity is the ratio between the vapor pressure, okay, the vapor pressure divided by saturation pressures. Now from the steam table, we find that the saturation pressure of vapor corresponding TD means corresponding dry bulb temperature 20 degrees centigrade, okay, corresponding the value of dry bulb temperature is 20 degrees centigrade. You can get the values, okay, that is basically 0.04242 bar. This is the PS. So as you know that phi, that is your relative humidity. Relative humidity is the PV divided by PS, and from the previous part of the numerical, that when you calculate the dew point temperature, so at that particular point we calculate the value of PV. So PV is basically, you know that 0.0170 and PS is your saturation temperature, saturation pressure, that is corresponding of the dry bulb temperature, that is 0.04242 bar. So that will be 0.40 or 40%. That is your relative humidity. Okay. And what is specific humidity? Specific humidity is basically relations with partial vapor pressure with barometer pressure. That is specific humidity as designated with W, and W is equal to 0.622 PV divided by PV minus PV. So 0.622 into PV means PV is your partial vapor pressure, that is 0.01701, which is calculated in your dew point temperature when you calculate, and PV is your barometer reading head, that is PB is a barometer reading, that is your 744 mm of Hg. 744 mm of Hg. That means you have to calculate, you have to convert into mm of Hg to that particular PV in terms of, sorry, so that is 0.017. Okay, so that is converted to 0. That is into bar. Okay, mm of Hg to the bar, so 0.986 PV minus of PV, that is 0.01701. So specific humidity W will be 0.0109 kg of dry air. So you just convert into kg of dry air. Kg of dry air, you convert into 10.9 gram per kg of dry air. Okay. So in the second part of the numerical, so this is the specific humidity. Okay, this is the specific humidity of saturation pressure. This is the specific humidity, and so this is the specific humidity. Now specific humidity. Now the last part of the numerical, that is basically degree of saturation. So when you calculate degree of saturation, you know that degree of saturation is equal to mu, and mu is the ratio of means W. W is basically specific humidity divided by specific humidity at saturation of saturated air. Okay, so W, as you know, the value of W is basically coming out, that is 0.0109. Okay, so W will be 0.0109. But what is the value of WS? Because WS is the specific humidity of saturated air. So that WS will be calculated from 0.622 PS divided by PB minus PS, because when PB means partial vapor pressure is shift to the saturation pressure, when it converts into PB to PS, then it gives you the specific humidity of saturated air. So Ws will be 0.622 PS divided by PB minus PS. Okay, so that will be 0.622 into 0.042 divided by PB. Value of PB is basically your barometer reading head, that is PB. Now PB is basically 0.986 minus PS, that is 0.042. So that will be Ws. Ws will be 0.027 kg per kg of dry air. Now in terms of Ws, you can get the value 0.027. So put these values here, so you can get the value of degree of saturation, that will be 0.391 or 39%. Okay, and we calculate the next part of the numerical, that is vapor density and enthalpy of mixture per kg of dry air. Okay. So in this part of the problem, we will calculate the vapor density and enthalpy of mixture per kg of dry air. Now you know that vapor density, as you know, the density is the mass per unit volume. You know that. Now you have to calculate the density, means vapor density. Vapor density means the density of vapor. Okay. Now as you know that, the formula of vapor density, when you calculate the vapor density, that is rho V. Okay, we know that the vapor density rho V is equal to W into PB minus PV divided by RA into TD. Okay, now W is your basically your specific humidity. Okay, specific humidity we already calculate in the last part of the numerical, that specific humidity is basically W, that is 0.0109. Okay, and PB is your barometer reading, that is 744 mm of Hg. You just convert it to bar. So 740 mm of Hg, when you can convert into it, that will be PV will be 0.986 minus PV. PV is your basically the vapor pressure. The vapor pressure will be 0.017 divided by RA into TD. So RA is equal to 287 into TD. TD is your 303. Now the vapor density, that will be, when you calculate, that will be 0.01216 kg per meter cube of dry air. So it means per meter cube of dry air, there are only vapor are present, that is basically 0.01216 kg. Okay, so per meter cube of dry air, there are only this amount of kg of vapor are present. So that indicates your vapor density. Now in the last part of the numerical, you have to calculate the enthalpy of mixture per kg of dry air. Now enthalpy of mixture, as you know that enthalpy of mixture of per kg of dry air, so this is a formula to calculate. As you know, we already elaborated these equations, that how we come that H is equal to 1.022 TD plus W into HFG dP plus 2.3 TdP. So TD is your dry bulb temperature, dry. So dry bulb temperature is given as your 30 degrees Celsius in the numerical. Okay, specific humidity, that is basically 0.0109, which is calculated in the previous part of the numerical, 0.0109, and HFG dP means corresponding dew point temperature. What is the latent heat of vaporization? So what is your dew point temperature? So dew point temperature is 15 degrees centigrade. We already calculated in the first part of the numerical. So corresponding of dew point temperature of 15 degrees centigrade, you have calculated the HFG dP. That dP is indicate that latent heat of vaporization corresponding dew point temperature, that is HFG dP. So that will be 2466.1 kilojoule per kg. Now if you put all these value, then you calculate H. H means your enthalpy of mixture per kg of dry air. That will be 57.95 kilojoule per kg of dry air. So if you put these values, TD in terms of 30 degrees centigrade, W is your 0.0109, and HFG dP, that will be 2466.1, and TdP is your dew point temperature, that is your 15 degrees centigrade. If you put all these values here, you can get the values 57.95 kilojoule per kg of dry air. Okay, so in this problem we will calculate that dew point temperature, relative and specific humidity, that is relative and specific, that is basically relative means phi, that is basically PB by PS. Okay, specific humidity, you calculate the specific humidity, that is your W. Okay, that is basically 0.622 PV by PB minus PW. Okay, PB minus PB. Degree of saturation mu. Okay, mu is 0 W by Ws. Okay, vapor density, that is your rho V, and enthalpy. So all this part of the numerical I have calculated, and okay. So now the topic is adiabatic saturation temperature. Okay. Now, as the name suggests, that adiabatic saturation temperature, so basically it indicates a temperature, first of all. Now, the temperature at which, so this is the temperature at which the air is basically in unsaturated condition is transformed into saturation state. That means the at which the temperature at which, basically it can be defined as adiabatic saturation temperature at which the air can be brought to saturation state, and the process should be in adiabatically. Okay, that's why this process is called basically adiabatic saturation temperatures. Now, first of all, is the air is normal air, which is in the atmospheric air. We know that basically it is in unsaturated air. Okay, so if it is unsaturated air, now if you change from unsaturated air to saturated air by means of adiabatically to reach actually in saturation state, so that particular temperature is called basically adiabatic saturation temperature, and it is also sometimes also called adiabatic saturation temperature or thermodynamic wet bulb temperature also. Now, so this is the arrangement for adiabatic saturation temperature. You can see here that inside in the arrangement that one insulated chamber there. So this is the insulated chamber, okay, in which the water are present. So water are already present here. Okay, so basically this is insulated because there is no heat transfer takes place during the process. So that's why it's insulated, and that's why the process is adiabatic, right? Now, so basically it's an insulated chamber in which the water is present sufficiently, adequately. And one more point here is one arrangement are there, that is makeup water. Okay, the makeup water arrangement are there because of when the evaporation process takes place, the water level content, it should be constant, so that the makeup water arrangement should be there. Okay, these are the arrangement part. So this is the first of all is the insulated chamber. This is the inlet port. This is the outlet port, and this is the water level, which is basically exit within the insulated chamber, and these are the makeup water. Okay, this is the makeup water level, makeup water which flow the water in the insulated chamber when the evaporation process takes place of water, when the unsaturated air is flowed through the inlet port through the long sheet of water. Okay, so this is the arrangement for when we explain the adiabatic saturation temperature. So this is the we can say that this is the arrangement for that. Now, but the definition is clear, is that the temperature at which the air can be brought to saturation state by adiabatically. Okay, then the temperature is called basically that adiabatic saturation temperature, or it is sometimes also called thermodynamic wet bulb temperature also. Okay, now what is the process for that? So as you know that, so this is the unsaturated air. As you know that air is maybe saturated air, unsaturated air. Now if the air is unsaturated in condition, that means the air has some capability to absorb more water vapor, but there are less amount of water vapor present. So at that particular time, that is basically in unsaturated air. Okay. Now this is the inlet port of the insulated chamber in which the air can pass through this channel. So this is the H1, W1 and PW1 that indicates that particular channel for unsaturated air. Enthalpy is H1, W1 is your specific humidity, and TD1 means dry bulb temperature at section 1. Now when the unsaturated air is transformed into saturated air by some means of thermodynamic processes, that at that particular time the enthalpy at particular section 2 will be H2, the specific humidity will be W2, and the temperature, that temperature is basically adiabatic saturation temperature, that also sometimes it's so called T2 or TW2, because it is also sometimes also called thermodynamic wet bulb temperature. Okay, and specific humidity is W2. But what is the change in specific humidity, we can discuss later. Is there specific humidity a change or it's constant, we can discuss on that. But this is the whole process for when we explain the adiabatic saturation temperature. But what is the process? Now let's take this. So this is the unsaturated air that enters at section 1. So first of all, unsaturated air enters at section 1. So this is section 1, this is section 2. Unsaturated air enters at these sections. Okay, now as the air passes through this through the chamber, okay, over the long sheet of water, okay, long sheet of water, what happens, that air, as it is unsaturated condition, so air should be capable to absorb water. Okay, so means water vapor. So there will be some evaporation process takes place. As the evaporation process takes place, so obviously at that particular time, first of all, the initial condition of for unsaturated air, the specific humidity is W1. Now when the evaporation process takes place, that means the water vapor content, evaporation process means the water vapor content is high. So at this particular time, the specific humidity also increases. So when the air is passes through this channel, so after that, so air passes through the chamber over a long sheet of air. Okay, now water evaporates. So in the water evaporates fine. Now specific humidity increases, because as you know that specific humidity is the it is basically defined the amount of water vapor present per kg of dry per kg of dry air. So what amount of water vapor present? So at that particular initial conditions, when there is no evaporation process takes place in unsaturated air, the specific humidity value is compared to less when the air pass through the water, over the water when the evaporation process takes place. So obviously there is specific humidity is increases because there are some amount of water vapor also increases, right? So this part is also covered now. So when the evaporation process takes place, obviously the water level will be decreased. So it should not be happen there. So that makeup water arrangement are there. So that makeup water is added to the chamber to make up water level, so that it constant, the evaporation process is constant throughout the process. So that's why makeup water level, so means makeup water are used to maintain the constant water level when the evaporation process takes place. Okay, now if at that particular time both air and water are added, okay, are basically cooled as evaporation process takes place, because there are some thermodynamic process are interchange, means energy transfer from air to water, water to air. So there is some energy transfer occurs. So at that time, obviously air and water both are cooled, because the evaporation process takes place in between them. Okay, so this process is continuous until the energy transfer is equal. So basically when they are reach actually steady state conditions. Okay, when they are steady state condition means when the unsaturated air reach from unsaturated condition to saturation state, that's time we can say that is a steady state conditions. So at particular time when the steady state condition are reached, the air flowing at section 2 is basically, so this is section 2 when it is exit from the insulated chamber section. So at that particular time the specific humidity is also increases. Okay, and as the specific humidity increases, obviously the air is reached at a particular steady state conditions, okay, or steady conditions, and obviously at that section the air is in saturated air. Okay, this is a saturated air, and at that particular time at which temperature this process is occurs, actually that temperature actually called adiabatic saturation temperature or thermodynamic wet bulb temperature. Okay, now if we look into this the TS part of this adiabatic saturation temperature, if you see that this is arrangement for that, as we know that this is unsaturated air, this is saturated air. for unsaturated air, the enthalpy is H1, W1, specific humidity and adiabatic temperature. It indicates when the evaporation process takes place, when the unsaturated air is passed through the long sheet of water, that basically state goes to the insaturated state or saturated air state. At that particular enthalpy is H2 and specific humidity is basically W2, and the wet bulb temperature or the corresponding temperature at which the unsaturated air is transformed or is changed in saturated air, that temperature is basically called thermodynamic wet bulb temperature or adiabatic saturation temperature. That temperature is designated T2 or TW2. Okay. Now, if you represent this phenomena in your TS diagram, what you see here, that this is your TS diagram, and this is as you know, this is the diagram. So, first of all, is when the air enters at section 1, so this is section 1 and this is section 2. Now, at section 1, the air is basically in unsaturated air in conditions, means air in it's in unsaturated in condition. Okay. Now, the evaporation process takes place, means there are some cooling process also takes place. Now there are one line is 1 to 2 that indicates basically that it's a basically adiabatic, this is the unsaturated air condition, and this is the adiabatic saturation process. It's adiabatic saturation process. Okay, adiabatic cooling process, you can say 1 to 2 is your adiabatic cooling process, in which you can see that is the process point 1 is your unsaturated air in condition, as the point when the process goes through the in between the insulated chamber. So there are some processes occurs, and when it reach at particular point at section 2, at point 2, that reach in the saturation state. So this process of this cooling process is basically from 1 to 2 is basically your the adiabatic cooling process or adiabatic saturation process, you can say that. Okay, and this process also indicate as constant pressure cooling process, and at that particular point, that point is basically dew point temperature, dew point. Okay, so corresponding unsaturated air, if you draw the diagram TS, so this point indicates your dry bulb temperature, as it is initial condition, that's why it is indicated as TD1. When it reached at final temperature or in temperature at which the unsaturated air is transformed into saturated air condition, that temperature is basically the final condition, you can say. That's why it is also sometimes called TD2, means dry bulb temperature at section 2, as it is a saturation, as it is in this temperature actually the saturation air we can absorb, so that's why it is also called wet bulb temperature. So TD2 is equal to TW. Okay, so in this process what happens, so these are a TS diagram in which you can see that there are some processor occurs, and these are at which you can, if you write the balancing the enthalpies of air which enters at section 1 at exit at section 2, you can write, so balancing the enthalpies of air at inlet 1 and at exit 2, that will be, so enthalpy that air enters at energy, that is H1 plus, so at that particular time specific humidity is here W1. When it exit from this condition, before this, when the makeup water, the water flows into the insulated chamber, there are some specific, because of that the evaporation process takes place, so there are specific humidity increases, that means the specific humidity will be W2 minus W1, okay, into HFW. HFW it indicate the sensible heat for water, okay, sensible heat for water vapor, so HFW that equal to H2, H1 plus W2 minus W1 into HFW is equal to H2. Now if you write this equation in this form also, H1 minus W1 HFW is equal to H2 minus W2 HFW, where H2 minus W2 into HFW is your sigma heat, okay, which is basically remains constant throughout the process. Okay, now, and as you know that the H1 is basically the enthalpy at section 1. So the enthalpy at section 1 is basically is your unsaturated, obviously, and the superheated condition also. Okay, so H1, if you write down H1, so H1 will be, you can write down also HA1 plus W1 into HS1, that indicates H1 is equal to the enthalpy. H1 is the enthalpy of unsaturated air. Okay, H1 indicates the enthalpy of unsaturated air. Okay, enthalpy of unsaturated air, and H1 basically the enthalpy of dry air, okay, at dry bulb temperature at TD1, that indicates HA1, plus W1 means at section 1 the specific humidity, okay, that is W1, and HS1, so at particular this condition at corresponding TD1 the enthalpy of superheated vapor, so S indicates the superheated, so HA1 means enthalpy of unsaturated air, that equal to HA2, HA1 that indicates the enthalpy of dry air at corresponding dry bulb temperature at section 1, plus W1 means there are some unsaturated, there will be some value for specific humidity, so that corresponding value is W1 into HS1, that indicates basically the enthalpy of superheated water vapor at dry bulb temperature TD1. Okay, similarly you can also write here H2 is equal to HA2 plus W2 into HS2. Okay, so as you know, H1 is equal to this one and H2 is equal to this one. So in this equation, you can write this equation in terms of H1 and H2 here. Okay, so here you can write here in terms of H1 this one, and in terms of H2 you can write this also. Okay, now if you do some you want to make some form, because if you want to know that what is the specific humidity when the air is in your unsaturated in condition, so you can calculate this way, that W1 will be ultimately W2 into HS2 minus HFW plus HA2 minus HA1 divided by HS1 minus HFW. So this will be the expressions to calculate the specific humidity at the inlet condition or the specific humidity of the unsaturated air. In similar fashion, you also calculate the saturation at particular when the air is basically in saturation state or saturated state. At that particular time, you can also this value, if you know the value of W1, HS2, HFW, all this value, you can calculate also W2 means specific humidity at the exit conditions. Okay, thank you very much for listening and watching me, and in the next lecture video we will discuss on that psychometric chart. Okay, and what is dew point temperature, what is the psychometric chart, what are the points of theirs, and what are the dry bulb temperature, what is dry bulb temperature occurs in your psychometric chart, what is wet bulb temperature, what is relative humidity, specific humidity, all these things will be discussed in the next lecture video. Okay, thank you very much for listening and watching me, and goodbye.